Okay, to be able to understand the concept of holography in details, I'm going to play you a short video about how conventional holography is recorded and reconstructed. Then I will explain this numerical reconstruction technique for this holography.
Special high-resolution photosensitive materials are used for the registration of holograms. The exposed holographic plate then undergoes photochemical treatment and drying. Let's put it into its previous place and illuminate it only with a straight reference beam. A holographic image of the object has been reconstructed.
As you saw in the video, there is a need to illuminate the sample again or photochemical sample again with this laser light. But in digital holography, we don't have a laser light for the elimination of the sample, for the elimination of the photosensitive film because it's a digital recording. So what we do in this case, we use numerical reconstruction, which is an alternative way to stimulate the light propagation. And we use mathematics to reconstruct the hologram, which is called a numerical reconstruction algorithm. Okay, so numerical reconstruction algorithm provide us quantitative phase image. This is the key uh, of this holography because the image is quantitative and is proportional to two factors. One is refractive index of sample, which is which represents the material inside the sample, and then second one is the thickness of the sample. If you look at this equation, the phase equation, we see that both parameters are included. So on the left side, you see a hologram, and then of this red blood cell and skin cancer cell, and then right side, you see this reconstructed hologram. So the unit is in the radian, and you can see the unit on the right side. This video shows a red blood cell fluctuation, which is recorded by digital holographic microscopy. As you can see, this cell is fluctuating, the membrane of the cell, and this fluctuation allows the body to absorb oxygen from the red blood cell and dispose dioxide carbon to the cell, which can be carried to the lung to be released from the body. Okay, so why this quantitative phase imaging signal is important? Uh, First of all, the signal is non-invasive. As I told you, in the fluorescence microscopy, you need to stain your sample with some dyes, but here, no staining is required. Uh, Second, DHM enables us to provide sample at single cell level, and then we can analyze single cell level result. Like I showed you previously in for the red blood cell fluctuation, we can study single cell. Most importantly, signal is quantitative and is proportional to both sample thickness and intracellular content. So, if any treatment can change this parameter like sample thickness or intracellular content, then we are able to observe changes in the signal. And also, imaging is fast and online. We can quickly reconstruct the image and then see what happens, or even we can see it online. And also, signal is quantitative and is meaningful, so no calibration is required. There are some disadvantages also, similar to the other microscopic techniques. One is that the thickness and refractive index difference are coupled together, and there are needs to decouple these values. Secondly, refractive index is the integral of refractive index on the direction of the imaging. So it's difficult to have the RI for different organ. Okay, here, let me show you a few more examples of red blood cell. Red blood cell is a very transparent object cell, so this one is used a lot in digital holography because it can give us more insight into the application of this type of microscope. So red blood cell, here you see a red blood cell. When the light passes through the red blood cell, it passes from one direction and then goes out from the other direction. That's why we see the red blood cell profile, 3D profile in this shape. In A, you can see a RBC sample. B shows a single cell, and D is a single cell presented in mesh form. C is a single cell presented in mesh form, and D shows a video of red blood cell under temperature shock. Let me play this for you. Okay, the original state, the red blood cell is at 17 degree. You can see the temperature here. The red one shows the original red blood cell. By the time goes, the temperature increases, and what happens here? The material, the media nearby the cell is releasing its water, is actually evaporating. So what happens here is that the tonicity level between red blood cell and then the media which is stored in will change. What happens here? The red blood cell releases volume, releases water to the slide, to the media, to preserve the tonicity level, and that's why you see the volume of red blood cell here changes. And what we see is in the dimple, there will be a dimple in the center of the red blood cell, which which can be observed by digital holographic microscopy. So now the temperature is 40 degree, almost 40 degree, which is very critical for the body. And in this case, if we go higher, sometimes we have irreversible changes to the red blood cell. But in this case, if we add some water to the media nearby the cell, then we can recover the cell shape. Okay. Okay, so I explained a little bit for you what is digital holographic microscopy and what is quantity phase imaging. Now I'm going to show you how AI, an automated computer algorithm, can help digital holographic microscopy. In this case, I'm going to show you red blood cell classification with machine learning and pattern recognition. Secondly, I show you cancer cell classification with two methods. One is deep image learning, and the other one is handcraft feature-based classification. Number three, I will show you how image-to-image transformation deep learning model can be used to remove noise in digital holography. And number four, I'm going to show you cardiac cell nuclear segmentation with deep learning in digital holographic microscopy. And number five, I'm going to show you how optical flow method can be used in calculation of cardiac cell speed with digital holography, and then we show application of drug treatment cardiac cell and its effects on optical flow, on speed measurement with optical flow.